Hey, welcome back to Under the Hood. Open Chrome right now and load 10 tabs. One tab freezes completely, but the other 9 keep working just fine. You probably never stop to ask why. Now open your code editor, your music app, and your browser at the same time. They all run independently. One crashes, the others don't care. But sometimes you write a program and one tiny bug kills the whole thing all at once. Not just one part, everything. And that comes down to one decision you made, maybe without even realizing it. Processes versus threads. Let's go under the hood. When the OS runs your program, it creates a process. That process gets its own virtual address space, its own file descriptors, its own memory. The kernel tracks all of this in a single data structure called the task struct. That isolation isn't just software. The CPU has a register called CR3 that points to the process's page tables. Every memory address your program uses goes through those tables. Another process has a completely different CR3. There is no way to reach across without the kernel explicitly setting it up. A thread is just another task struct but created with one key difference. It shares the same page tables as its parent. Same heap, same globals, same file descriptors. The only things it owns are its stack and its CPU registers. Creating a process means copying the entire page table tree. That takes time, and it scales with how much memory your process uses. Creating a thread skips all of that. It just sets up a stack and points at the same address space. That's why thread creation is 10 to 30 times faster. But sharing memory is exactly what causes race conditions. Even a single increment counter ++ compiles to 3 CPU instructions: load, add, store. The scheduler can cut in between any two of them. 2 threads, 2 cores, same memory. One write disappears. So a process gives you isolation at a cost. A thread gives you speed at a risk. The question is, what does your program actually need? When you spawn a process, the kernel calls fork. It copies the entire page table tree, every level, every entry. Your child process gets its own address space before it runs a single instruction. Threads skip all of that. They call clone, with one flag, clone VM. That tells the kernel to share the existing address space instead of copying it. No duplication, no setup. That's the entire reason thread creation is 10 times faster than fork. Once they're running, the scheduler sees no difference. Linux's CFS keeps a sorted tree of tasks by how much CPU time each has consumed. It always picks the one that got the least. Process or thread, it doesn't matter. But switching between processes costs more. Every switch loads a new value into CR3, the register that points to the page tables. That flushes the TLB, your CPU's cache of address translations. Every memory access after that is a miss until it warms up again. Switch between threads in the same process and CR3 stays the same. TLB stays warm. You're just swapping registers and a stack pointer. That's why high-performance servers use thread pools instead of forking per request. 2 tools: fork for isolation, clone for speed. Which one you need depends on what your program can afford to lose. Chrome runs each tab as a separate process, not a thread. If one tab hits a bug and segfaults, the kernel kills that process. The other tabs keep running because they have different page tables. That's the isolation you saw in the hook by design. Now take Python. Python has a global interpreter lock. Only one thread can execute Python bytecode at a time. So if you spawn 10 threads to crunch numbers, you still get one core. To actually use multiple cores in Python, you use the multiprocessing module, which calls fork, and gives each worker its own address space. Apache used to fork a new process for every incoming request. Each request got full isolation, but fork is expensive and memory usage stacked up fast. Nginx took a different approach. It uses a fixed pool of worker processes, and inside each worker, it handles thousands of connections using non-blocking I/O on a single thread. Less overhead, same isolation at the worker level. Most modern web frameworks use a thread pool inside a single process. Your Node, JS server, your Go HTTP handler, your Java servlet container. One process, many threads, shared heap. Fast to spin up, fast to context switch. The trade-off is that a memory corruption bug in one handler can take down the whole server. So the pattern is the same everywhere. You reach for processes when a crash should not spread. You reach for threads when you need speed and you trust your code. The first gotcha is assuming threads are always faster than processes. If your code is CPU-bound and you're in Python, adding threads makes it slower. The GIL serializes them. You get the overhead of context switching with none of the parallelism. The second one will ruin your day. If you fork, after spawning threads, only the calling thread survives in the child. Any mutex that was locked by another thread at the moment of fork stays locked forever. No one can unlock it. Your child process deadlocks silently. Threads share memory, which means any global variable, any shared counter, any cache is a potential race condition. You don't have to be unlucky. On a multi-core machine, two threads can write to the same address at the exact same time. Without a lock, the result is undefined. When a child process exits and the parent never calls wait, the kernel keeps the process entry alive in the process table. It's dead but not gone. That's a zombie. Enough of them and you run out of PIDs. Your system stops being able to create new processes. Processes and threads are simple concepts with sharp edges. The bugs they produce are subtle, hard to reproduce, and expensive to debug. Know which tool you're using and what it costs. That's it for this one. Thanks for watching, and I'll see you in the next video.